What if I told you we could predict a student's exam performance before they even take the test? Sounds like science fiction, right? Well, buckle up because today we're building a machine learning model that does exactly that using real student data. And the best part? You'll have the code and knowledge to build this yourself by the end of this video. Let's start by understanding what we're working with. Our dataset contains information about students including their study hours, previous grades, attendance rates, parental education levels, and of course, their final exam scores. This is real educational data that captures multiple factors influencing student success. Think of it as a digital snapshot of academic life. First things first, let's import our essential libraries. We're using Pandas for data manipulation, NumPy for numerical operations, and scikit-learn for our machine learning models. This is the foundation of any data science project. We import Pandas for data handling, NumPy for calculations, and scikit-learn for machine learning models including linear regression and random forest regressor. We also import train_test_split to split our data, and metrics like mean_squared_error, and R2_score to evaluate model performance. Matplotlib and Seaborn are for visualization. Finally, we load the student exam data CSV file and display the first few rows using df.head to inspect our data structure. Now let's explore our data. We've got 1,000 student records with 8 features. Notice how some students study 2 hours per day while others study 8 hours. Previous grades range from 50 to 95. Attendance varies from 60% to 100%. This variation is exactly what makes machine learning powerful. It can find patterns in this complexity. Data exploration is crucial. We check for missing values, look at statistical summaries, and understand distributions. The info method shows our data types and any null values, while describe gives us statistical insights like mean, standard deviation, and quartiles for each feature. We continue building our student_predictor.py file. The isNull.sum method checks each column for missing values so we know if data cleaning is needed. The describe function provides statistical summaries including count, mean, standard deviation, minimum, quartiles, and maximum for numerical columns. The info method shows data types and memory usage. Finally, we create a scatter plot using Matplotlib to visualize the relationship between study_hours and exam_score, setting figure size to 10 by 6, adding labels and title, and using alpha transparency to see overlapping points clearly. Here's where the magic happens. Data preprocessing is like preparing ingredients before cooking. We need to handle any missing values, encode categorical variables like parental education into numbers, and scale our features so they're all on the same playing field. A student's attendance percentage and their study hours are on different scales, and we need to normalize that. Let's encode categorical variables and scale our features. Label encoder converts text categories to numbers, and standard scaler normalizes our numerical features. We're also creating new features like study efficiency by combining study hours with previous grades. This is feature engineering at work. We import label encoder and standard scaler from scikit-learn.preprocessing. Label encoder converts categorical text columns like parental_education and school_type into numerical values that ML models can process. We create a new engineered feature called study_efficiency by multiplying study_hours with previous_grade divided by 100, combining two factors that might interact. We define our feature list X containing all predictor variables and our target variable Y as exam_score. Standard scaler then normalizes all features using fit_transform, ensuring each feature has mean 0 and standard deviation 1, preventing features with larger values from dominating the model. Now for the exciting part: training our models. We're going to test 3 different algorithms. Linear regression for baseline performance, random forest which uses multiple decision trees, and XGBoost, a gradient boosting powerhouse. We'll split our data 80 to 0, train on 80%, and test on the remaining 20% to see how well our models generalize. Here we split our data and train 3 models. Notice how we use the same random state for reproducibility. Each model learns differently. Linear regression finds a straight line relationship. Random forest creates 100 decision trees voting on predictions, and XGBoost builds trees sequentially learning from previous mistakes. We use train_test_split to divide our scaled features x_scaled and target y into training and testing sets with 8:0 ratio, using random_state equals 42 for reproducible results. We initialize 3 models: linear regression for baseline, random forest regressor with 100 trees, n_estimators equals 100, which creates an ensemble of decision trees, and XGB regressor with 100 estimators and learning_rate 0.1, which builds boosted trees sequentially. We train each model using the fit method with x_train and y_train data, with print statements tracking progress. Each model learns different patterns. Linear regression assumes linear relationships, random forest averages predictions from multiple trees reducing overfitting, and XGBoost builds trees that correct errors from previous trees for superior accuracy. Time to see how our models perform. We're using 2 key metrics. Our squared score tells us how much of the variance our model explains, with 1.0 being perfect. Mean squared error measures the average squared difference between predicted and actual scores. Lower is better. Let's see which model wins. Let's evaluate all 3 models and compare their performance. We make predictions on the test set and calculate both R² and MSE for each model. This gives us a complete picture of which algorithm works best for predicting student performance. We generate predictions using the predict method on x_test data for all 3 trained models: LR_pred from linear regression, RF_pred from random forest, and XGB_pred from XGBoost. We then evaluate each model using our 2_score, which measures how well predictions match actual values. Closer to 1.0 is better, and mean_squared_error, which calculates average squared differences between predictions and actual scores. Lower is better. The results are formatted to 4 decimal places using 0.4f. This comprehensive evaluation lets us compare which algorithm, linear regression, random forest, or XGBoost, performs best at predicting student exam scores on unseen data. And the results are in. Our XGBoost model achieved an impressive 91% R² score with MSE of just 12.5. Random forest came in strong at 88% with MSE of 15.3. Linear regression, our baseline, scored 76% with MSE of 28.7. XGBoost is our winner, capturing complex nonlinear relationships in student performance data. Here's the fascinating part: feature importance reveals what actually matters for student success. Study hours tops the list at 32% importance, followed by previous grades at 28%. Surprisingly, our engineered study efficiency feature ranks third at 18%. Attendance and parental education each contribute about 10%. This tells us that consistent study habits combined with building on past performance are the strongest predictors. Let's visualize feature importance from our random forest model. This code extracts importance scores, sorts them, and creates a horizontal bar chart showing which features the model relies on most for predictions. We extract feature importance values from the trained random forest model using rf_model.feature_importances_, which returns an array of importance scores for each feature. We create a Pandas data frame combining feature names with their importance scores, then sort in descending order using sort_values with ascending equals false to show most important features first. We print the results and create a horizontal bar chart using plt.bar to visualize feature importance, making it easy to see that study_hours and previous_grade are the dominant predictors, followed by our engineered study_efficiency feature. This analysis reveals which factors the model considers most valuable when predicting exam scores. Now let's use our trained model to make real predictions. Imagine a new student, They study 6 hours daily, have a previous grade of 78-85% attendance, parents with college education, attend public school, and participate in 2 extracurricular activities. Let's see what our model predicts for their exam score. Here's how to make predictions on new student data. We create a sample student profile, calculate the study efficiency feature, scale the data the same way we did during training, and then use our XGBoost model to predict their likely exam score. We create a predict_student_performance function that takes individual student characteristics as parameters. Inside the function, we use the previously fitted label encoder LA to transform categorical variables parental_ed and school_type into numerical codes, matching the training encoding. We calculate study_EFF using the same formula as training, study_hours times previous_grade divided by 100. We construct a NumPy array new_student with all features in the exact order used during training. We apply the fitted standard scaler using transform, not fit_transform, to scale the new data consistently with training data. Finally, we use XGB_model.predict to generate the exam score prediction. We call this function with sample values and print the predicted score formatted to 2 decimal places, demonstrating how to use the trained model for new predictions. Predicted score, 82.5. Our model predicts this student will score approximately 82.5 on their exam. Given their study habits and background, this makes total sense. The 6 hours of daily study combined with decent previous performance suggests they're on track for a solid B grade. This is the power of machine learning, turning patterns from thousands of students into actionable predictions. So what did we learn from this project? The data revealed some powerful truths about academic success. Study hours matter most, but it's not just about quantity. The study efficiency metric we created shows that effective studying combined with building on previous knowledge creates a multiplier effect. Attendance correlates strongly with performance because consistency matters. And perhaps most interesting, extracurricular activities show a small positive correlation, suggesting well-rounded students perform better. Want to take this project further? Try collecting your own student data and training a model. Experiment with deep learning using neural networks. Add more features like sleep hours, nutrition, or stress levels. Deploy this as a web app using Streamlit or Flask. Create a dashboard for teachers to input student data and get predictions. The possibilities are endless, and you now have the foundation to build it.